A 30-minute documentary narration by Richard C.J. Young. C. Jung. Part 1. The Materials We Abandon. There are two things happening simultaneously in the American built environment right now, and almost nobody is putting them in the same sentence. The first, landfills across the upper Midwest are filling with post-consumer plastic that nobody has a serious use for. HDPE from milk jugs, polypropylene from yogurt containers and bottle caps, PET from water bottles and takeout packaging. These are collected by recycling programs, sorted, baled, and then, in many cases, transported significant distances to be sold at commodity prices that barely cover the collection cost. The economics of post-consumer plastic recycling are brutal. The material exists at massive scale. The demand for it, in finished form, is thin. The second, the housing industry is running out of cheap structural materials that actually hold up. OSB warps when it gets wet. Wood rots when the envelope fails. Hardie board cracks on impact and requires a regimented painting schedule to maintain warranty. Every one of these materials is installed by skilled tradespeople on a job site exposed to weather, delays, and human error, and every one of them carries a warranty that expires well before most people finish paying off their mortgage. Now put those two things in the same sentence. Post-consumer polyolefin, the plastic sitting in bales in a materials recovery facility right now, has a thermal conductivity approximately 4 times lower than wood. It does not rot. It does not absorb moisture. Termites cannot eat it. It does not require the painting schedule that fiber cement demands. When it reaches end of life, it can be processed and remolded, not recycled into a park bench, but remolded into the same structural panel it just was, at the same specification, with the same performance. The question has never been whether you could build with recycled plastic. The question has always been whether you could make the economics work at a price point the market would accept, with a product that a builder would specify without apologizing for it. That is the question the ECOFRAME project answers. The answer is yes, but only if you build the right product for the right market tier with the right manufacturing process, and only if you are honest about every constraint before you spend a dollar. Part 2. Why nobody solved this before. The honest question is why, if the economics are this clear and the material has been sitting in bales for 30 years, nobody has already done this. There are 3 answers. Each one is a specific technical barrier that blocked every serious attempt, and each one has a specific solution that did not exist at this cost until recently. The first barrier is thermal expansion. Polyolefins expand and contract with temperature roughly an order of magnitude more than wood. A south-facing wall in a Wisconsin year swings from -20 to 120 degrees Fahrenheit, and neat polyolefin moves enough across that range to buckle a rigidly fastened panel and pull the fasteners out of the framing. Every early recycled plastic cladding prototype failed here. You cannot simply screw a plastic panel to studs and expect the wall to stay flat through a season. The solution in the EcoFrame panel is 2-part. The fly ash-filled matrix cuts the coefficient of thermal expansion of the composite roughly in half compared to neat polyolefin. The mineral filler constrains the polymer at the molecular level. The residual movement is absorbed by the snap-in tie channel, which permits controlled microsliding along the seam rather than transmitting the force into the fasteners. The panel moves. The wall does not buckle. The second barrier is fire. Unfilled recycled polyolefin burns readily, with a flame spread index and smoke development profile that no building code in the country will accept in an exterior wall assembly. This single fact killed more recycled plastic building product startups in the 1990s and 2000s than every other cause combined. The solution is the silane-treated fly ash, which does 2 things under heat. It acts as a thermal mass that slows the temperature rise of the polymer, and at the surface, it forms a ceramic char layer that interrupts the flame front and starves the combustion of the polymer underneath. Paired with a halogen-free intumescent flame retardant in the stabilizer package, the composite reaches a flame spread performance that passes the International Building Code threshold for exterior wall assemblies in the market tiers the product is sold into. Not Class A, not yet. But Class B, with a documented test path to Class A in the next compound iteration, which is the credential the architectural premium tier requires. The third barrier is the one nobody outside a polymer lab talks about, and it is the reason every attempt that tried to add mineral filler to recycled plastic ended up with a weak, crumbly panel. Fly ash and polymer do not bond. Pour fly ash into molten polyolefin and you get a mixture, not a material. The fly ash particles sit in the polymer like sand in jello. The panel is weaker than either component alone because the filler introduces stress concentrations at every particle boundary and the polymer cannot transfer load across them. This is the delamination problem, and it is the wall that stopped every serious prior attempt at a structural recycled plastic composite. The solution is the maleited polyolefin coupling agent, a 4-weight % additive whose functional groups bond covalently to the fly ash surface on one end and entangle into the polymer chains on the other. It is, at the molecular level, an adhesive that welds the filler to the matrix. Without it, the panel is a science fair project. With it, the fly ash becomes a reinforcing agent that actually stiffens the composite and improves its fire resistance at the same time. There is a fourth barrier that is not technical. It is manufacturing. Structural foam injection molding on recycled feedstock at panel scale is a process that required a specific combination of equipment, a co-rotating twin-screw compounding line feeding a structural foam press through a balanced valve gate hot runner that existed in fragmented form across the industry but was not assembled into a single validated process flow for a building product until the last decade. The equipment is not exotic. It is refurbished, available, and within the capital budget of this project. But the integration is the work, and the integration is done. That is why nobody solved this before. 3 technical barriers, 1 manufacturing integration, and the discipline to use post-consumer flake instead of the virgin pellet that every prior attempt retreated to when the recycled feedstock got hard. Each barrier now has a solution documented in the dossier. None of them required a breakthrough. They required the specific combination run in sequence at the right cost. Part 3. What the product is. The EcoFrame panel is a 4-foot by 8-foot structural Rainscreen panel, 1.5 inches thick, made from a recycled polyolefin blend, shipped flat in a standard dry van trailer without oversized permits. Let me take that apart precisely. The core material is post-consumer recycled plastic, 65% HDPE, 20% polypropylene, 15% PET, sourced as washed post-consumer flake from certified materials recovery facilities. To that base, you add 2 things. The first is silane-treated North American Class F fly ash at 25 weight %. Fly ash is the fine particulate byproduct of coal combustion, a material that currently goes to landfill or is stockpiled in surface impoundments at power plant sites across the country. Silane treatment activates its surface chemistry so it bonds covalently to the polymer matrix rather than sitting as an inert filler. The second is a maleited polyolefin coupling agent at 4 weight %. This is the molecular adhesive that ties the fly ash particles to the polymer chains at the nanoscale. Without it, the composite delaminates under stress. With it, the fly ash becomes a true reinforcing agent that stiffens the matrix and improves its fire resistance. Inside the panel, hidden, never touched on site, is a 2-gauge welded wire steel mesh running in a dual plane, embedded 1/4 inch off each face. The mesh is the reason this panel achieves structural performance rather than merely cladding performance. It adds 550% bending stiffness over the unreinforced composite. The panel can carry real loads, resist racking forces, and function as a structural element in a load-bearing wall assembly. The building geometry is an A-frame, 20 feet wide, 36 feet long, slant wall height 24 feet 2 inches. The A-frame is not an aesthetic choice. It is a load path decision. The inclined walls simultaneously serve as roof and wall surface. Snow load sheds under gravity. Rain sheds. The geometry distributes load through the inclined plane without requiring a separate roof structure built above vertical walls. The A-frame uses less material to enclose the same habitable volume as a conventional rectangular box. There is one transportation constraint that the A-frame creates, and it must be named directly. A 24-foot slanted wall section is a superload under interstate transportation regulations. You cannot ship a completed A-frame wall assembly across state lines without oversized permits, escort vehicles, and route approvals that vary by jurisdiction. That constraint is not a problem. It is the manufacturing model. You ship 4-foot by 8-foot flat panels, legal on any standard dry van, and you assemble them on site. A crew of 3 to 4 people one day. no cranes, no special equipment. The flat pack model is not a concession to a logistics limitation. It is the correct engineering answer to that constraint, and it produces a better on-site experience than any pre-assembled alternative. Part 4, how it is made. The manufacturing process is a two-stage system running in sequence. Stage 1 is compounding. A 35 to 40 millimeter co-rotating twin-screw extruder with a 44:1 length to diameter ratio processes the raw material streams, the post-consumer plastic flake blend, the silane-treated fly ash, the maleited coupling agent, the UV stabilizer package, and the halogen-free flame retardant into a homogeneous pellet feedstock. The co-rotating twin screws melt, mix, and distributively disperse the components. The fly ash achieves uniform distribution in the polymer matrix at the micron scale. The output is underwater pelletized into uniform, dust-free pellets that flow freely into the Stage 2 hopper. Stage 2 is structural foam injection molding. A 1,200-ton refurbished structural foam press, a Battenfeld or equivalent, takes the compounded pellets and injects them into a single-cavity P20 tool steel mold via a dual-nozzle, balanced valve gate hot runner manifold. The endothermic chemical blowing agent, sodium bicarbonate-based, at 1.5 weight%, activates during the injection phase. It releases carbon dioxide gas inside the melt front, expanding the polymer and reducing the clamp tonnage required to fill the mold. It eliminates the sink marks that would otherwise appear on the face surfaces of a section this thick. The resulting panel has a slightly cellular interior core, which improves the insulation R value, and dense solid face skins with uniform surface finish. The mold is P20 tool steel, not aluminum. Aluminum molds are faster to machine and lower in cost. They are also not appropriate here. A panel this size, run at commercial volume, will cycle the mold hundreds of thousands of times over the equipment's working life. P20 at 48 to 52 Rockwell hardness handles that fatigue. Aluminum does not. The seam system is where the patentable intellectual property lives. Every panel has a molded groove running the full length of both long edges. A snap-in hidden steel tie channel is pre-seated in the groove of one panel during final inspection and ships with the panel. On site, the crew tips up the next panel and slides it into position. The tie channel slides into the receiving groove of the adjacent panel as a direct consequence of the tipping motion. Steel continuity across the seam, the load transfer path that allows an 8-foot post grid rather than a 4-foot grid, is established by the act of assembly. No tools, no extra hardware, no skilled labor. One motion. The tie channel is galvanized or stainless steel because it lives in the 3/4-inch vented Rainscreen cavity behind the panel face, and the Rainscreen cavity is the wet zone. Bulk water management happens there. Condensation occurs there. The channel must not corrode. Its geometry is designed so it seats under gravity as the panel tips. Self-aligning, self-locking. Production capacity for the initial factory installation: 40 panels per 8-hour shift, 1 shift per day, 5 days per week. 840 panels per month. This single factory, running 1 shift, serves the entire continental United States through standard freight. Part 5, the competitive landscape. To understand where this product fits, you need to understand what it is competing against, and more importantly, what each competitor cannot do. OSB, Oriented Strand Board, is the dominant structural sheathing in residential and light commercial construction. It costs $12 to $28 per panel at retail. It is everywhere. It is also moisture sensitive in ways that are now well documented. OSB exposed to prolonged wetting delimits, swells, and loses structural integrity. It is not a suitable exterior cladding surface. Every builder using it on wall sheathing is managing a moisture vulnerability, not solving it. The EcoFrame panel does not compete with OSB in price. It replaces the function that OSB was never supposed to serve in the first place: exposed, weather-facing structural cladding. Hardie board, fiber cement siding from James Hardie, is the premium volume product in exterior cladding. It costs approximately $1.50 to $3 per square foot installed. It requires painting on a 6 to 10 year cycle to maintain warranty. It cracks on point impact. It cannot be field cut without creating silica dust that requires respiratory protection under OSHA guidelines. It is heavy, about 2.5 pounds per square foot, which drives installation labor cost. The EcoFrame panel is lighter. It does not require painting. It will not crack on impact from a hammer or a tree branch. It can be field cut with a standard circular saw. Cedar and engineered wood siding occupy the architectural premium tier. Cedar at $6 to $12 per square foot installed. Engineered wood at $4 to $8. Both require periodic maintenance. Both are organic materials in a wet environment. Both carry warranty provisions that shift liability to the installer once field cutting occurs. The EcoFrame panel enters the premium structural Rainscreen tier, $265 to $395 retail per 4-foot by 8-foot panel, or approximately $8 to $12 per square foot at the architectural premium tier, and beats every competitor on moisture resistance, maintenance schedule, and end-of-life recyclability. Not on price. On performance, on lifecycle cost, and on the credential that the green building market is actively paying a premium for. Verified post-consumer recycled content in a structural application. The green building market is not a niche. LEED certified construction represented over 20% of new commercial construction starts in the United States as of the most recent data. Passive house construction is growing at double digits annually. Municipal affordable housing authorities in cities with sustainability mandates are under obligation to specify recycled content materials when performance equivalence can be demonstrated. This product demonstrates performance equivalence and surpasses it on several metrics. That is the competitive position, not the cheapest. The best credentialed structural Rainscreen in the market tier that already pays for credentials. Part 6. The economics and the grant stack. The unit economics are fully closed, built from first principles. The fully loaded cost of one panel is $138.72. That number includes direct materials at $98.48, accounting for post-consumer plastic flake, fly ash, coupling agent, blowing agent, UV package, flame retardant, the steel mesh, the seam gasket, and the tie channel. It includes labor at $11.10 per panel at Wisconsin prevailing wage rates for one shift. It includes energy at $3.11, consumables at $1.85, facility overhead at $3.39, and equipment amortization on a 7-year straight-line basis at $20.79. That cost is real. It is not a pro forma estimate. It is built from vendor quotes, comparable equipment depreciation schedules, and Wisconsin industrial energy rates. The selling price depends entirely on the market tier you occupy. Commodity positioning, attempting to compete with OSB at $12 to $28 per panel, is arithmetically impossible. The material cost alone is $98.48. Do not attempt it. Premium structural Rainscreen positioning, competing with Hardie board and engineered wood siding, places the wholesale price at $195 per panel, retail at $265. The gross margin is 28.8%. Break-even is 217 panels per month. Capital recoup on the full equipment investment is 31 months. Architectural sustainable premium positioning, the preferred strategy, places wholesale at $295, retail at $395. Gross margin is 53%. $156.28 per panel. Break-even drops to 78 panels per month. Capital recoup falls to 11.2 months. The architectural premium tier is not aspirational. The product's credential stack supports it. Post-consumer recycled content at 65% minimum. Fly ash diversion from surface impoundment. A manufacturing process that consumes no virgin polymer. Those credentials are what LEED point calculators, passive house certifiers, and municipal sustainability procurement offices are actively scoring. Total capital requirement for the initial installation, $1,894,000, with a 20% contingency included in the equipment line items. The equipment stack, compounding line, structural foam press, P20 mold, induction preheater, flattening jigs, racking, mechanical and electrical infrastructure, is fully itemized to that number. A joint venture with a regional wood plastic composite manufacturer or recycled plastics compounder absorbs approximately $365,000 of that total, 25%, in exchange for manufacturing capacity access. The out-of-pocket raise after the JV closes is $1,529,000. The grant stack for this project is not speculative. It is mapped to the specific project profile and the specific funding program eligibility criteria. USDA Rural Energy for America program, REAP, provides grants of up to 25% and guaranteed loans for renewable energy and energy efficiency projects at rural small businesses. A rural Wisconsin manufacturing facility producing a structural product with measurable energy efficiency benefits qualifies. REAP awards grants on a competitive application basis twice per year. EPA Solid Waste Infrastructure for Recycling, SWIFR, provides grants for projects that improve solid waste and materials management infrastructure. A manufacturer that is the end market for baled post-consumer HDPE and polypropylene, the exact materials that recycling programs have the weakest end markets for, is an archetypal SWIFR applicant. Wisconsin Economic Development Corporation Technology Development Loan, WEDC-TDL, provides below-market rate loans for Wisconsin manufacturers at the commercialization stage. A first production mold and molding press, backed by a locked engineering dossier and a defined proof panel test protocol, is a WEDC-TDL eligible project. Federal SBIR Phase 1, Small Business Innovation Research, provides $150,000 to $300,000 for early-stage technical validation. The ASTM E72 proof panel test is an SBIR Phase 1 deliverable by definition, a bounded, milestone-based validation of a novel structural system. Combined, the non-dilutive grant stack has the potential to cover $300,000 to $600,000 of the $1.53 million capital raise before the equity conversation begins. Part 7. The build sequence and who this is for. The pitch sequence runs in exactly 5 steps, and the sequence is non-negotiable. Step 1. Lock the specification. Complete. The engineering dossier, 8 queries covering material matrix, panel geometry, deployment model, seam system, manufacturing process, proof panel protocol, unit economics, and grant mapping, is finished and filed. Step 2. Produce the render video. A 3-dimensional animation of the snap-in tie channel mechanism is the single most important pre-revenue marketing asset the project has, showing how the tie preseats in the groove, how the panel tips up, and how the steel continuity is established by that one tipping motion. That animation replaces 1,000 words in every investor conversation. It costs very little to produce. It must exist before any external pitch meetings happen. Step 3. Secure the joint venture. A regional wood plastic composite compounder or recycled plastics processor with an existing twin-screw compounding line is the target. One value proposition: contribute your compounding capacity. We contribute the product design, the mold, and the molding press. You receive a percentage of revenue on every panel that runs through your line. You absorb 25% of the capital requirement in exchange for a manufacturing partnership that uses equipment you already have and creates a new revenue stream at no risk to your core business. Step 3 is the hard boundary. Before it closes, no personal capital goes into engineers, attorneys, prototype fabrication, or testing. Everything up to Step 3 is time. Everything after Step 3 runs on partner capital. Step 4. Fund and run the proof panel. The ASTM E72 transverse wind load test. 2 panels, an 8-foot mid-span seam connection, no structural post behind the seam, 300 pounds per linear foot racking load, is the gate between concept and fundable asset. Budget: $12,500 to $15,500, covered by the JV partner. 2 outcomes: pass and the 8-foot post grid is confirmed, or fail and the post grid defaults to 4 feet with the product still viable. Either outcome produces data. Either outcome has a path forward. This single test is the most important milestone in the entire project. Not the mold, not the factory, the test. Step 5. Lock the grant stack and the capital raise. With proof panel data in hand, the USDA REAP application and the WEDC TDL application both have the empirical structural performance data they require as supporting evidence. The equity raise of $1.53 million has a validation event to anchor the pitch deck. The timeline from Step 5 to funding close: approximately 6 months. This video has been built for one specific audience. Not the retail customer, not the home buyer. The people who can write the check that makes the proof panel happen, and who want to be on the right side of the next generation of structural building materials before it becomes the standard. The opportunity is a specific gap, between what OSB and Hardie board offer, materials that rot, crack, burn, and go to landfill, and what architects, green builders, passive house designers, and municipal housing authorities have been asking for a decade. The specification is locked. The dossier is complete. The unit economics are closed. The patent position on the snap-in tie channel is uncontested in prior art. Everything is ready. The only thing left is the partner. If that is you, a WPC compounder, a recycled plastics processor, an impact investor in building materials, a construction materials operator with capacity and capital, the conversation is ready to happen. By C.J. Run at Twitstorm. Look, listen, or read in order to. C.J. Run. End. The ECOFRAME Blueprint. 30-minute narration script. Richard C.J. Young. C.E. Young.